Hey guys, today we will continue in our series where we go through the courses in FPGA Academy, and today we will continue with Lab 3, Latches, Flip-Flops and Registers. We have finished Lab 1 and Lab 2, and last time we looked at Quarters simulator, Questa. You can find this video on my YouTube channel, because today in Lab 3 we will use Questa to simulate our designs, and also you can find part 1 and part 2 on my YouTube channel. And we will continue with Lab 3. Part 1. Intel FPGAs include flip-flops that are available for implementing a user's circuit. We will show how to make use of these flip-flops in part 4 of this exercise. But first, we will show how storage elements can be created in an FPGA without using its dedicated flip-flops. Figure 1 depicts a gated RS Latch circuit. A style of VHDL code that uses logic expression to describe this circuit is given in Figure 2. So we will try to design this circuit, and we can design this circuit using this entity. If this latch is implemented in an FPGA that has 4 input lookup tables, then only one lookup table is needed, as shown in Figure 3a. So if we have FPGA that has lookup tables with 4 inputs, we can design this circuit using only one lookup table. Although the latch can be correctly realized in one 4-input lookup table, this implementation does not allow its internal signals, such as these signals and these signals, to be observed because they are not provided as outputs from the lookup table. To preserve these internal signals, in the implemented circuit, it's necessary to include a compiler directive in the code. In Figure 2, the directive keep is included by using VHDL attribute statement to instruct the Quarters compiler to use separate logic elements for each of the signals. Compiling the code produces the circuit with 4 lookup tables depicted in Figure 3b. So we'll try our compiler to use 4 lookup tables instead of 1, and to do this we will use attribute keep for all of these signals, and we will say that signal is true to preserve the signal. So first we will create a new Quarters project. I have already done this. Generate a VHDL file with the code in Figure 2 and include it in the project. Okay, so let's do that now. I have my Quarters project here, and we will try to implement the code given here. Okay, so we will have 3 inputs: clock, R, reset, and S as set. It will be STD logic, so just Boolean values. And then we have Q as output, and it will also be STD logic. Then we have our signals. We define signal RG, RG, SG, and then QA and QB, also as STD logic. And then we define our attribute keep. It will be of type Boolean. Attribute keep of, and then we copy all of these signals. Signal is true. And then we will try to implement this. So we will have RG, then we will have SG, then QA and QB. And also our final output will be just QA. So RG, that's this signal, that will be R and clock. R and clock. Our SG will be S and clock. QA will be not, and here will be OR, and it will be QB or RG. You can copy this here, and here it's gonna be S and QA. So that's our design. We can try to compile. And let's look at what we have to do next. Okay, we have some error. Let's look at, okay, semicolon, semicolon. Let's try now. Compile the code and we have it set as top level entity. So compile the code, use the Quartus RTL viewer tool to examine the gate level circuit produced from the code, and use the technology map viewer tool to verify that the latch is implemented as shown in figure 3b here. So let's use RTL viewer, and here we can see that we have our AND gates, our OR gates, or NOR gates here. Here we have our NOR gate. So that's exactly as shown here. We have our AND, our NOR. So that's correct. And let's look at technological map viewer. And we can see indeed we have 3 inputs, then output, and we have 4 lookup tables instead of 1. And these lookup tables are exactly as shown here. So FPGAs include flip-flops that are available for implementing a user circuit, but we are not using these flip-flops. We are using storage elements without using the dedicated flip-flops. So we are using lookup tables. Simulate the behavior of your VHDL code by using the simulation feature provided in the model sim software. I will be using Questa, but it will be almost identical if you use model sim or Questa. And I will use the way how to simulate that I have shown in the previous video. So here I have my Questa application, and I will go to my file with all the designs, FPGA Academy, Digital Logic, and Lab 3, and Questa. And here I can show you I have created Lab 3, Questa. So I have created TCL script, TCL part 1. So I have created this script. So we quit any simulation that is currently running. Then we create our library work, and then we compile VHD designs. In our case, that's part 1. Then we have our test bench, and the test bench is provided in FPGA here in design files. And then I have my wave, so we can look at this wave, and you can see I have added some RS QA/QB signals, and that's all. I have changed this, and I have used the one we have used in the previous video. So that's all of the changes I've done. So I've created TCL, then VHT is provided by FPGA Academy, and then I have created wave part 1 do configuration file. So now we can just run do and testbench part 1.tcl, and if I run this, you can see here I have my signals, and if we look at the simulation here, it's the same as here. So we have our reset and set, and our output QA and QB, and QB is just inverse to QA. And we can see that in the beginning we have reset set to 1 and set to 0. So, and before I can explain how RS Latch actually works. So this is the design we have implemented, and whenever clock is set to 1, so clock in this case works as enable. Whenever clock is set to enable, basically set to 1, the RS Latch works as follows. So if both inputs are 0, it's latched. That means it will remember the state from the previous from the previous state. So if we set reset to 1, then it will be resetted to 0. If we set to 1, it will be 1. And if we put if both inputs are 0, then it will remember the state 1 or 2 from the previous one. And if both of them are 1, that's invalid state, and in that case it's unstable and we don't know what output we will get. So we should avoid setting both of them to 1. Now we can look at our simulation. We have reset and set here. So we have reset set to 1, so our output is 1 here. And then here we have set to 1 and reset is 0, but our clock is 0, so nothing changes until the clock gets to be 1. Here the latch is enabled, and we can see that our QA changes to 1, and here set goes to 0, but again our clock is 0. When the clock is 1 again, both of them are 0, which means nothing changes. It remembers the state. And here again, clock is enabled, and we can see reset is 1, so it gets resetted to 0 again. So this is our simulation, and we can continue. We have done this, so let's look at part 2. Figure 5 shows the circuit for a gated D-latch. So this is D-latch, and I can again show you what D-latch does. So it's the same as the circuit above, basically, but the difference is that we connected reset and set to 1, and we inversed this signal, which means that when D is set to 1, this input signal, we get 1 as output here, and if it's 0, then it's set to 0. And of course we have to get our clock to be 1 when that's happening. If it's 0, then the D-latch is not enabled, nothing changes. And we will try to implement this now. Create a new Quartus project, generate a VHDL file using the style of code in figure 2 for the gated D-latch. Okay, in figure 2, so we will use this structure and use the keep directive to ensure that separate logic elements are used to implement the signals. Okay, so let's do that now. Let's close this. I'll create a new file and call it part 2. Part 2. And I'll copy the code from part 1. So part 2, and we will not have 2 inputs, we will have just 1 input, D, and now we will create this code. So let's do this. So I'll delete all of these, or we can just delete these. QA will stay the same, and yeah. So basically, yeah, so we will have our SG, and SG will be not, and here will be AND, and it will be clock and S. Then we will have our RG, that will be not, and it will be this is not S, this is D in our case, and this will be not D and clock. So that's this. And then we have our GA, and that will be not, and here we'll have AND again, and it will be AND QB, and here we will have SG. We have to put semicolon at the end. And QB, that's this one. That will be not RG and QA. So we have implemented this. Let's set it as top level entity and let's try to run it. We can do start compilation and analysis. We don't have to compile the whole project. We can just do compilation and analysis. Compile your project and use technological map viewer tool to examine the implemented circuit. Okay, let's examine the result. You can see again we have 4 lookup tables, and we can also look at RTL viewer, and we can see that we can compare this with the circuit. So we have here AND, that's here, and then AND here. Then we have NOT, and here we have AND, but here we have NOT and not here. So that's correct, and not here and not here. And then we have 2 ANDs here, and they have NOT after them. So these 2 circuits are exactly the same. Verify the latch works properly for all input conditions by using functional simulation. Okay, let's do functional simulation. So we will do new, and here I will use university program VWF, and here I will do edit, set end time, and let's set this to, let's say, 20 nanoseconds. Then we say insert node or bus, node finder, and we will list all of these and input them. So we have our D and Q, and we have D and Q, but we also need and clock, of course. And now I will do simulation settings, and here I have to change one part to make this work on my computer. So I have to change this part. Here I have to change this to this. Save. And now we can, this is gonna be right clock. Period will be 2 nanoseconds, and the let's do count value, or what can we do here? Arbitrary value, but I want to set it after some time, so let's do count value, and we will count to 1, or count every 10 nanoseconds. So like this. Or you can actually do clock with period 4, like this, or clock with period 5 maybe, so it's a little bit irregular. And now we can run our simulation. So let's look at the simulation. So this is our output. And we can see when D, our input, goes to 1, nothing changes because clock is set to 0. As shown here, we have to have clock set to 1 for this to change. And when D is 1, and it will basically, we will see the output, input on the output. So let's look at quarters. So here clock goes to 1. We can see that it goes to 1. Here on the clock it goes to 0, so it goes to 0. Here it goes to 1 again, and it stays 1 until here, where it goes to 0. And this continues. So we can see it only changes when clock is 1, and also only changes when clock is 1. So this seems to work correctly. So we have done our functional simulation, and we can continue. Create a new quarters project which will be used for implementation of the gated D-Latch on your DE series board. This project should consist of a top-level module that contains the appropriate input and output ports for your board. Initiate your latch in this top-level module. Use switch 0 to drive the D input of the latch and use switch 1 as clock input. So we have our part 2. And we can just change this to, we can have 2 inputs. We can have switch as input. This switch will be a STD logic vector, and it will be 9 down to 0. And then we want to show it on LEDR. So LEDR, and this will be the same except for this. And we can set our output to LEDR 0, and our input will be here. So this will be switch 0. And this will be switch 1. Switch 1 and switch 0. So let's try to compile this. Include the required pins, test the functionality. So now we will try to test the functionality. Part 3, part 4, part 5. So seems to work. Let's look at part 3. Circuit for a master-slave D flip-flop. Okay. Almost done. Let's go to program. We can see DE SOC board, auto detect, select our chip, which is this one. Okay. And select output files, program, and program. So if we look at our code, we can see that, or if you look at here, our D, that's our switch 0, and this is switch 1, and we show this output on Q. So right now you can see right now it's turned on. So if I switch clock to 1, which means enable, and D will be 0, it goes to 0. If I set this to 1, it works. If I put the clock down, it remembers the state. The switch doesn't do anything. And again, if I put this clock as 1, it turns off. And I can turn. So, works correctly. So today we have implemented RS Latch and D Latch. And next time I will finish this video. So next time we'll look at part 3, master slave D flip-flop, and also part 4 and maybe part 5. So this is gonna be all for today's video. If you wanna see next parts, don't forget to subscribe, and I'll see you in the next one. Bye.